Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. My name is John Goodall, and I'm at the Nicholas School of the Environment at Duke University. So I'm going to be a slightly different perspective on all this. I am a scientist. I have a background in civil engineering and water resources engineering. The title of my talk today isn't exactly what I'm going to focus on. I'm going to try to take a little broader look at the hydrologic sciences and water research community and how we want to use informatics and computers to better our research. So I thought I'd start with just a definition of what is hydrology, since it's a pretty diverse crowd here. And this is a definition from the National Research Council panel. So the hydrologic cycle you can think of. Where is water? Where is it going? What kind of contaminants is water transporting as it moves through space? So recently there's been a grouping of hydrologic sciences to better organize ourselves in terms of the research that we do and presenting kind of a common interface to the funding agencies. So this is the Consortium of Universities for the Advancement of Hydrologic Science, or CUAHSI. So it's just a few years old now, but it's already grown to about 100 universities. And there are 4 real organizing elements of CUAHSI, and I'm going to cover 3 of them here real briefly. The first is hydrologic observatories. So these are watersheds approximately the size here. So these are about 24, I think, proposed hydrologic observatories. And what we'd like to do is use these as sort of digital watersheds or digital environments where we can synthesize and fuse all types of data that's already being collected by satellites and by national agencies, and deploy our own sensor networks and sensor arrays into these environments to get a higher resolution picture of where water is going and how it's transformed as it moves through space and time. I should say that none of these are actually in place yet. It's sort of at the proposal stage at this point. So again, instrumentation. There's a lot of data that's already being collected at this watershed scale that hydrologists could use to do science, but it's really difficult for us to take all that information and fuse it together into one common picture. And so on the left here is sort of what we already have, and of course we would like to put in new sensors, have control over where those sensors go. The measurement devices that are in the field now, or the location of them, are largely selected by the federal agencies, and scientists aren't really consulted on where to put those particular gauges. So they're of value, of course, but of limited value. So what's the need for CUAHSI? How do we justify ourselves? Well, there's a large societal need. Again, how do we meet water demands right now as the population grows, as climate change situations occur? How do we provide water of a good enough quality, and also our environment? How do we provide enough water to keep our environment healthy as well? And how do you balance all those demands? And there's a scientific goal as well. Just understanding the flow of water. Where does it go? How long does it stay in certain stores within the environment? How long does it stay in the groundwater, the atmosphere? How does it transfer? Again, how are pollutants transferred, and the biogeochemicals cycle related to the hydrologic cycle? But what's new about CUAHSI? I mean, this has been done before with the hydrologic sciences. We're trying to take a larger scale look at these things, an entire watershed. Instead of a very small field study of high resolution, how do we do this? How do we scale it up to an entire watershed so that we can better present our conclusions to policymakers and to inform policymakers about the management of water? I'll just continue on. So now I'm going to focus right now on the informatics part of it. of CUAHSI. So there's a prototyping research going on right now that was funded by the National Science Foundation, and these are the partners of that research grant. I was at the University of Texas. I just completed my PhD there, and I'm now at Duke, so I get to continue working on this, which is fun for me. It's an interesting project to think about and to really design how hydrology will occur over the next 10 or 20 years. So what are the 4 goals of the CUAHSI HIS? The first one, and one we've been focusing on mainly, is just better access to data. I'm going to show some slides later on where we actually did a user assessment, and we asked scientists how much of your research time do you spend just getting data and getting it pre-processed so that you can actually do some analysis. And it's a surprising amount of time that the scientists spend doing those basic little things. Again, the Hydrologic Observatory, this digital watershed. How do we create the seamless picture where me as a scientist can kind of log in and say, well, I want to know where total nitrogen was measured, search through time and space and find those observations and get access to those data. And hydrologic science. So how would an informatics infrastructure really help hydrologic science improve insights of how these water cycles are occurring? And of course, education is also a big component of this research, of this project. How do hydrologists convey the ideas of the water cycle to their students in the classroom? So as I mentioned before, we did a user assessment just to get a sense of what our field looks like. How do they use computers right now, and what would they like to be able to do? So this pie chart right here shows we sent out 100 surveys and we got 76 responses from 39 universities. And we asked the scientists to first identify what their field was. So you can see how diverse CUAHSI is. About 30% or so say they're water resources, or surface water hydrology, and it kind of tails off after that. A very diverse field. What operating system to use? This is kind of interesting. We're big Windows users. You could identify multiple operating systems. So there are 20% or so that are using other operating systems, but we are definitely Windows people. And also, well, what software packages or languages do you find useful? And just as Jim mentioned in his talk, Excel is top of the list here. ArcGIS, a GIS software package, and then a bunch of computer languages. What's interesting here is the last one, ModFlow, is the only hydrology model listed. So what you'll find in hydrology is everyone has their own model that they programmed during their PhD, and they still use it. And so there's no adoption of a single model. And that's actually something that we'd like CUAHSI to be able to help with, get a real community together and have a community model. So as I said before, how much time do you spend preparing your data, just getting the data and preparing it? So we had about 20% say less than 10% of the time, and the 44% saying about 10% to 25%, and nearly a quarter are saying somewhere between 25% and 50% of my time is spent trying to massage the data to get it ready for analysis. So that's obviously time not spent on doing analysis, not spent doing on hydrology. And the other downside of this is all those kind of pre-processing steps are the same. So, I'm sure if you're a bunch of hydrologists got them in a room together, and most of them have some kind of algorithm or written an Excel spreadsheet to convert daily stream flow to monthly stream flow. And so we could just have one kind of community web service or whatnot to do simple processing like that. I mean, simple things like that would really help our community. So to more detail is, what are the things that the problems when you try to integrate data in hydrology? Inconsistent data formats. Metadata is not there. irregular time steps or spatial scales. So again, rescaling data in space and time. Just little mundane tasks that we spend a lot of time doing. So the kind of the vision for the CUAHSI HIS, and this follows on with the previous talk, this is where we'd like to go. Have some kind of workflow sequencing, web portal where we have a library of models and data manipulation routines, and we can string those together to get access to data, do some computations on the data. So this is kind of the vision of where CUAHSI HIS would like to go. So now I'm going to talk about just one example of the National Water Information System, which is all the stream flow information that the USGS collects. There's about 100 years worth of daily time series for a couple 100,000 gauges in the U.S. And there's also real-time data, groundwater levels, water quality information. So if you're a hydrologist and you want to get some stream flow data, what do? You go to this website, you go through a list of a series of websites to kind of isolate what information you want. Eventually you get to a page with the data. You copy that data down to your disk. You do some parsing of it, put it in Excel or whatnot, and then you're ready to go and do your science. So what I did is develop a web service that goes and kind of automates that task. So first, before I talk about the web service, so this is the XML schema for a particular station within the USGS. So a site number, a name, a lat-long location, the what HUC it's in, which is the watershed that station is in, and this is just the default list you get. There's actually 57 attributes for a USGS station. And again, so you construct a URL, and there's some logic in how you construct a URL. So the web service basically is just wrapping how you construct that URL and then how you parse the page that comes back. But you eventually, through the web interface, construct a URL, and then you get back this kind of text ASCII file. So again, the web services here basically automate that task so you can query for data within NWIS, within client applications, and not have to go through the web interface. Which, of course, isn't that mind-blowing for this crowd, but for hydrologists, it really is a whole paradigm shift. I can automatically get my data into Excel without having it going to NWIS, and that's a real helpful thing. So what I built was a GIS application that uses this web service to do plotting, and there's a workflow sequencing in ArcGIS called Model Builder, and so tools to go and do generic processing and to get access to NWIS and to other data sets that are relevant for hydrologists. So if I just show a demo here real quick. So this is the ArcGIS interface. Again, this was number 2 on our list of what software do you like to use the most. And it's just a little toolbar here where you essentially select what layer you want to plot for. You can point the data source to either like a local database and formatted according to a data model called ArcHydro, which is it's basically an ASCII data or Access database, or you can point it off to the web. So this is going straight to the NWIS web. And then you just basically point and click, and it will chart the stream flow. It's just using Microsoft Office to chart it here. So again, not a big deal for you all, but if you show this to hydrologists, they get fired up. And they say, wow, that was easy. I get access to this data a lot easier. And then you can go on the chart and say, oh, I really like this. I want to save it to export it to Excel. I mean, this is where we are, to be honest. So so let me continue on with actually, let me show one more demo. So we're working with the San Diego Supercomputing Center to help us on the IT side of things. And they've built a website. Reza, actually, who's here in the audience, built the website. So I'm going to fire that up. So this is a web portal where hopefully we can coordinate our activities with the HIS and have a web interface that's similar to the desktop application I was showing before. So I could zoom into a particular area. I'm going to go into the Neuse River Basin here. So it's on a prototyping server right now, so we're purchasing a new server, so it's a little slow. But we can go, so we can have different sources here and say EPA stored or Ameriflux or whatever data sets we want. Very nice user interface because we've come to expect that in hydrologic sciences, a very nice user interface and straightforward. So you can click on a point, it will go off to NWIS and say, well, what time series are available for this point? And then within this environment, you can go and plot the data or download the data. Eventually, this will evolve into a whole workflow sequence where you can automate the go and get the data, do processing to the data, run a hydrologic model on that data. That's where we'd like to go eventually. So this is, might have picked one without data on it. But in any case, you get the idea. So, continuing on. So obviously there's more data in hydrology except for the NWIS data. There's the EPA store, Ameriflux, rainfall data. So those are just time series. So a place in time with a collection of daytime values. And those are relatively easy to transfer over web services. But when you start talking about grids of data, so climate model data, terrain data is gigantic. So we need to start thinking about how do you request information, keep it on a server, and then on that server be able to do processing and issues like this, which I'm sure you guys have answers for, but things that I've been thinking about. Geometries are also very important to hydrologists. Where are the watersheds, the water bodies, the river reaches? So how do web services interact with geometries as well? And then all the processing, geotemporal processing, aggregation of space and time, interpolation of space and time, how close are two objects within space and time, hydrologic processing, rainfall runoff, flow routing, those types of things, and visualization, of course. So this is the computer science perspective on how this whole thing will work, and I'll explain what I know of this. So basically my part is, what I've shown is this little piece here of getting data from national databases that already exist. And we would like to have sensors as well in the network where we can go and easily get data from sensors and tell sensors when to collect data and have models that talk to sensors. And a hydrologic model says, well, I need more information about the soil moisture because that would really help my model to improve its predictive abilities. So you could go and talk to sensors and collect that information. We could have geoprocessing and statistical processing stored on servers, ArcGIS server or R server, and then so if I'm a scientist and I'm not a GIS guy, you'll hear that a lot from scientists, but you can have access to geotemporal processing or geospatial processing that using ArcGIS server. So where are we going in terms of what I've talked about here with NWIS? Well, there's a lot of other data sets we'd like to get access to. So we need to standardize how you describe a hydrologic time series. What's the XML schema that we're going to use? How do you translate between how USGS describes a time series and the EPA describes a time series? How can we develop kind of a generalized but standard interface, an API, a WSDL file for getting access to time series? And the questions I have that I hope to have answered here, or at least discussed here, are what about large data sets? How do we deal with web services when we have large data sets? And how does the grid architecture, I've heard a lot about the grid, but how do I get access to that? How do I use that and if I wanted to do some science, and how does this play into the grid architecture? So again, the standards, there's a lot of standards out there. Do we grab one of the standards that are out there to describe a time series? Do we kind of piece these together to make our standard? Or do we support multiple standards? Probably support multiple standards. And so we need to develop the algorithms to convert between standards and whatnot. And then how do you describe this API, this generic API for accessing time series? Well, we like to think of the time series in 3 dimensions, space, time, and parameters. So slicing and dicing the space-time parameter cube and saying, well, I want to get what parameters were measured within this spatial domain over this temporal domain. Go and tell me where those were measured, what features have those. Now go get the time series for those particular features, those types of things. So that's my talk, and are there questions? Yeah. No, yeah, I mean, so I understand that you can keep a large data set on a server, but are there to transfer it from one server to another? Maybe I have that large data set on one server, but my processing algorithm's on another server. So there's OpenDAP is a protocol popular in this for transferring multi-dimensional arrays. How does that play into SOAP? I've had conversations with the OpenDAP people, and they're going to support SOAP eventually, but I'm sure there's answers out there. I'm not saying that these are questions that haven't been answered, but questions that I would like answered for me personally. Yes?
First, I wanted to compliment you on that interface for searching the geospatial data, the geodata, the hydrological data, actually.
Mm-hmm.
Because that's exactly the same sort of thing that our users want
Mm-hmm.
from our portal.
Okay.
They can't really download their 50 gigabyte files into Excel. And
Right.
They do want to be able to download pieces of it.
That's exactly right.
Search and explore. We have some similar tools.
Yeah.
As far as moving big data sets around, I don't know if SOAP has got
Yeah.
but there are other protocols.
Right.
Some ways that may work with, we use grid FTP.
Okay, that's what I've heard. Yeah.
So it's not even clear if that's always
Okay. Okay.
that allows a clear partnership.
I see. Yeah. Interesting. Yes.
You mentioned the use of archive math services.
Yeah.
Excel. Can you speak to the use of open source software versus commercial software within your specific community?
Our community, if you look at the list of software packages, it's almost all commercial packages. And you can think about why that is. Well, hydrology is kind of a small community, and we don't have a lot of resources or time to develop or to maintain open source products. So it's kind of, at least my impression, that we've kind of bought into commercial products and using commercial products. GIS, there's a slide I didn't actually show, but we asked, what GIS software do you use? It was 97% ArcGIS. And for your first choice, nothing else came in. It was either you use ArcGIS or you don't use GIS at all. For your second choice, you see some like GRASS is one that pops up, an open source GIS. But at least in our community, it's not widely used at all. As far as which way should we go, of course, open source would be a nice solution if we could build and maintain and have enough organization within the hydrologic sciences to organize a pretty massive open source endeavor. So there's got to be a balance, I think, though, between the two. Mm-hmm. Yes.
We've got fairly similar GIS needs, but the things are they just sort of match them. We started
Yeah.
with our IMS, but
Right.
we get
For server side, open source is there's not really very popular desktop or GIS system, but for server side, I've definitely seen like the one you mentioned and others pop up. So we have a project at Duke mapping marine mammals, and they are using an open source GIS web interface for doing that. Mm-hmm.
It seems like one thing you really want to make sure of, though, is that your formats are open.
Mm-hmm. Yes, the schemas, the XML schemas and whatnot. Mm-hmm. And so I think the best solution for us is to, again, a balance. So we use other commercial companies' APIs. So ArcObjects is the ESRI API, or Excel, or MATLAB. But we kind of have our own open source software that makes smart use of commercial software as well. So there's probably some balance that's the best solution for our community. Yes, Reza. Mm-hmm. Yes. Yes.
How to go about missing data when some of your stations fall down?
Yeah, that's a great question. Right now, if you click on a map and there's a missing data, then it's just you're retrieving the data for a particular station. So it should be smart about how it makes the map. So you should say, map the places that have total nitrogen over this time domain over this spatial domain, and then it goes off to NWIS and says, okay, these are the points, here's their lat long, go plot that in the GIS. So that's probably how we would handle, but we're not doing it right now. Yes, Jim.
I have a question about geometry. I have a model. Most of my models start out with initial conditions,
Yeah.
and then they go forward in time.
Mm-hmm.
And in both your case and in the weather case, you're getting real-time feeds.
Mm-hmm.
And you'd like to evolve what you're measuring with the model.
Yep.
And none of the models seem to allow me to recalibrate the current state
Mm-hmm.
to the measured state,
Mm-hmm.
so that I can go forward and
Mm-hmm.
start again.
Mm-hmm. So,
How do you guys deal with that?
well, I can talk about one example. At Duke, there's a professor, Ken Rickow, who does a lot of Bayesian statistics and updating. So his models have the sole goal of kind of incorporating that knowledge you gain from observations along with a statistical framework in a mathematical framework for routing and moving pollutants through the environment. So that data assimilation type of stuff it's also something we'd like to be better at in hydrologic sciences. I think the atmospheric scientists are further along on those types of issues than we are. But again, I think it would require a real community model and a community effort to build such a model that is capable of going and gaining access to real-time information and incorporating that into how it makes predictions. But yeah, the models that we have right now don't really support that. Mm-hmm.
The atmospheric science guys do have a way of taking updating the boundary conditions
Mm-hmm.
simulation to make the right correction. But I'm not sure how far along they are. But they do use it, or they are using it. They also use it in ensembles. They will launch 500 different variations, and then they launch the weather. And then based on which, this one goes that way and the weather's going this way, show that
Great. That's cool.